Okay, let's take a look at how to find the Lagrangian from a given Hamiltonian. Here's the question we're addressing. We're given the one-dimensional Hamiltonian for a classical particle with mass m. It's defined as h equals p squared over 2m times e to the power of minus x over a plus v of x. Here, a is just a constant with the correct dimensions. The task is to find the corresponding Lagrangian, and we're given 4 possible options. So we need to figure out which one of these is the correct Lagrangian corresponding to our given Hamiltonian. Let's dive into the solution. Our goal is to find the Lagrangian L starting from the given Hamiltonian H. We are given the Hamiltonian H equals p squared over 2m times e to the power of minus x over a plus v of x. Remember the fundamental relationship between the Hamiltonian H, which is a function of generalized coordinates q and generalized momenta p, and the Lagrangian L, which is a function of q and generalized velocities dot q. That relationship is h equals p times dot q minus L. In our specific one-dimensional case, the generalized coordinate q is just x and the generalized momentum p is p. So the relationship becomes h equals p times x dot minus L. Here x dot represents dx by dt. We can rearrange this equation to solve for the Lagrangian L. It's simply L equals p times x dot minus h. Now to use this formula, L equals p times x dot minus h, we need to express p in terms of x and x dot because the Lagrangian is typically written in terms of coordinates and velocities, not momenta. We can do this using one of Hamilton's equations. Recall that x dot is equal to the partial derivative of the Hamiltonian h with respect to the momentum p. Let's calculate that partial derivative from our given Hamiltonian h equals p squared over 2m times e to the power of minus x over a plus v of x. We need to take the partial derivative with respect to p of this expression. Looking at the terms, v of x does not depend on p, so its derivative with respect to p is 0. The first term has p squared. The derivative of p squared with respect to p is 2p. So x dot equals the partial derivative of h with respect to p, which is 2p over 2m times e to the power of minus x over a. We can simplify the 2's there, giving us x dot equals p over m times e to the power of minus x over a. Great. Now we have the equation x dot equals p over m times e to the power of minus x over a. Our goal is to solve this equation for p. We can simply multiply both sides by m and by e to the power of x over a. This gives us p equals m times x dot times e to the power of x over a. Now we have p expressed in terms of mx dot x and a, which is what we needed. Okay, let's go back to our formula for L equals p times x dot minus h. Now we substitute the expression we just found for p, which is m times x dot times e to the power of x over a. So L equals m times x dot times e to the power of x over a times x dot minus the entire expression for the Hamiltonian, which is p squared over 2m times e to the power of minus x over a plus v of x. Let's simplify the first term. X dot times x dot is x dot squared. So L equals m times x dot squared times e to the power of x over a minus p squared over 2m times e to the power of minus x over a plus v of x. Now we need to substitute the expression for p into the p squared term that's inside the Hamiltonian part of our formula for L. Remember, p is m times x dot times e to the power of x over a. So p squared will be mx dot e to the power x over a square. Let's substitute that in. L equals m times x dot squared times e to the power of x over a minus mx dot e to the power x over a square over 2m times e to the power of minus x over a plus v of x. Now let's square the term in the numerator. Mx dot e to the power x over a square becomes m squared times x dot squared times e to the power of 2x over a. So the expression becomes L equals m times x dot squared times e to the power of x over a minus m squared times x dot squared times e to the power of 2x over a, or divided by 2m times e to the power of minus x over a plus v of x. Start by simplifying the term inside the parentheses. This involves cancelling a factor of m and combining the exponential terms. The term inside the parentheses simplifies as shown on the slide. Next, we substitute this back into the expression for the Lagrangian L and distribute the negative sign. Now, observe that the first two terms are like terms. We can combine them by grouping the coefficients. Combining these like terms, we get 1 minus 1 half times our common factor. 1 minus 1 half is simply 1 half. Thus, the simplified Lagrangian is L equals 1 half times m times x dot squared times e to the power of x over a minus v of x. Now we have the derived Lagrangian. Let's write it using the dx by dt notation for x dot. L equals 1 half m times dx by dt squared times e to the power of x over a minus v of x. Let's compare this with the options given in the question. Comparing our result, which is 1 half m dx by dt squared e to the power x over a minus vx, we see that it exactly matches option number 1. In conclusion, by starting with the given Hamiltonian and using the relationship between the Hamiltonian and the Lagrangian along with Hamilton's equations, we derived the corresponding Lagrangian. The final result for the Lagrangian is L equals m over 2 times dx by dt squared times e to the power of x over a minus v of x. This matches option 1. The final answer is option 1.